company called GTEC, and I want to tell you today a little bit about what we do, about our brain-computer interface solutions, which devices we have to do that, and yeah, you can have a look, maybe to try out one of the systems later on. So shortly I want to introduce the company. 20 years ago, the two bosses of the company, they studied also at the university, did their PhD at the University of Graz. There is a biomedical engineering department with a specific department for brain-computer interfaces. And yeah, first ideas were created at the university already, but then they said, okay, we have to start a company to sell this equipment also to other researchers. So yeah, since this we already started with several other companies right now. So the original company is still based in Austria, but we have now already, for example, a location in Barcelona, one in the US, one in Hong Kong, to simply have better relation to our customers and to our research cooperation partners. So, yeah, probably you know where these locations are, but I gave this presentation also already in other countries where they don't even know where Austria is located. So our main fields are to develop all this equipment that is necessary to measure the signals from the human body, like the brain signals, but also like other signals, like ECG, activity from the heart, EMG, like muscle activity, or other signals. And we develop a lot of software interfaces for development of your own application. So we have a lot of rapid prototyping environments like MATLAB, Simulink, but also others like Python, C++, and so on, where people are able to get access to the data and then can do a development of their own application. But on the other side, we also produce our own applications for BCI. So yeah, as I said, we founded the company around 20 years ago. It's private, and now we are around, I think, 65 people overall. Over all of these years, we also participated in a lot of research projects. This is only an overview of some of them. Research projects mostly in Europe, with a lot of cooperation partners from different countries, also from France, for example, where we develop different interfaces, like here in this BETA project, for example. It was the goal was to develop a brain-computer interface for rehabilitation of stroke patients using robots, or here this one for a BCI for locked-in patients to see if there is how high their consciousness level is and what opportunities they still have or not, and others. So generally, when we speak about a brain-computer interface, we have always a subject or a patient where we are measuring the brain signals, so EEG or ECOG. ECOG is when it's invasive, so when you are measuring from inside the brain in principle, so a surgery is necessary. But usually we use systems like here, simply like this cap. You put it on your subject. You have here these electrodes that are responsible for the measuring, and this allows you to measure the brain signals on your scalp here, on the top of your head. And the computer is then analyzing these signals. So therefore, to measure this, you need an amplifier. So here at the Institute, this one is used, for example.
Yes.
So that you bring the signals from here to the computer, because the signal is very small, and this amplifier is bringing the signal from an analog to a digital signal. And the brain-computer interface is then analyzing the signals, and you want to control a device using these signals. The device can be the computer itself, so let's say, okay, I control the cursor on the screen, for example, using my brain signals, or I control a big robot, so there are several opportunities. Important is always that the device is giving a feedback to the patient, so that the patient or the subject can see, okay, I control with my brain signals this robot, for example, or the cursor. So this feedback loop is closed, which is, for example, very important when we are speaking about rehabilitation of patients. Therefore, this is very important, but also for other applications. I go quickly over this. So there are several methods, of course, to measure brain activity. We decided to use the EEG, but there are also others like fMRI or PET scans or magnetic encephalogram. These two are pretty expensive devices. Usually they're only in hospitals, pretty big, and it's very hard to do an analysis in these machines. There are other methods which are already very good. So near-infrared spectroscopy, or shortly NIRS, you measure activity of the blood flow in your brain using optical sensors. Here it's a little bit a timing issue for some applications, so that's why it's a good method, but we are not 100% fine with that for BCI. And ECOG, as I said, it's invasive, so electrodes in the brain. The signal is of course very good, but you need a surgery, and therefore it's hard to find volunteers to do that. Shortly an overview here for EEG and ECOG. So as I said, usually for EEG we use this kind of caps with electrodes. It can be only one electrode, but usually we use around 8 or up to 64 of these electrodes. And the signal range that we are measuring usually is between 0 to 40 hertz. Compared with ECOG, you can see here on the picture, this is the head of the subject. They make a small hole in the scalp, and they put these so-called electrode grids on the surface here. You can see here are the wires coming out from the brain directly. So yeah, as I said, it's invasive. Here you can see this electrode grid. All of these red circles are electrodes where you measure the signal. The advantage here is, of course, you don't have all these bones and so on in between. Therefore, the signal range is much higher, so you can measure up to 200 hertz or more, which gives you more opportunities than EEG. So you can measure high gamma activity, it's called, and yeah, the signal to noise ratio and spatial and temporal resolution are way better. But yeah, as I said, a surgery would be necessary. Some typical examples for applications of a brain-computer interface. So on the left top, it's a spelling system. There are characters or icons on the screen that are flashing up, and this can be used, for example, for communication for patients who cannot communicate anymore, but their brain functions are fine, like ALS patients, for example. The second one is mapping of the cortex. This is with an invasive method where we check when there is a patient with a brain tumor, for example, and you want to remove this tumor. You want to see which area or this area where the brain tumor is, for what is it responsible for. So, for example, when the brain tumor is directly over the area for your language generation, and you remove this area, then maybe you cannot talk after the surgery. So you want to figure out that before. so to don't remove any parts that are highly important. Then of course you can control like arm prostheses. So this is a pretty old picture here, but I think the idea is you can see. You can use it for applications in like a smart home control, so to control your home environment. You can use it for gaming. There are installations with art, like for music control. Of course, control of big robots. You can use the system in virtual reality environments, like here in France there is a group from Bordeaux, for example, a team of Fabien Lott, who is doing a lot of things in this direction to move around in a museum, for example, in a virtual one. And the last picture is rehabilitation of stroke patients. So after stroke, when one side is affected, cannot be moved, you can control with the brain-computer interface these movements, for example. Shortly, an overview of several systems that we have. The first one is our standard device with 16 channels. That's the one that is also here in the lab. Then there is a smaller device, for example, that is mobile, using a Bluetooth connection. The last one here is the oldest one, first one that was developed at the university still, also with 16 channels. Then we have multi-channel systems with up to 256 channels, so a lot of electrodes on the cap. Can also be used for these invasive recordings. Then we have wireless systems now also. So in case of the wireless system here in the back, this one, this small box is in principle like this, only a small version, where you have no cables any longer, only to the electrodes, and the signal is transferred through Wi-Fi to the computer. This can also be used with dry electrodes. So in this case, the electrodes don't need any gel. These electrodes are with gel, so we have to inject here a little bit of gel so that the signal can be measured. With the dry sensors, that's not even necessary, so you simply put on the cap and can directly start afterwards. This is with 64 channels wireless system, for example. That's, in case of wireless, the maximum that we have at the moment. A new development is with NIRS. That's a combination. So you have here in the back still the standard EEG system, but on top we have a cooperation here with Artinis. It's a company that is producing these NIRS parts, to have synchronized NIRS and EEG signals. This is environment in Simulink, for example, where we can see here are the signals from the EEG system and here are the signals from the NIRS system. Everything is processed in one model, for example. As I said, we have different interfaces for the development, like MATLAB API, Simulink, and so on. So not so important here. With all of these, you have access to the data, of course, of the signal, and you can process the data afterwards. So we use for our prototyping a lot the Simulink library because it's gives us already a lot of functionality, but we add also our own functionality here to do analysis of the signals. So in principle, when we are talking about a complete setup, this is an overview. We have several amplifier solutions and several electrode solutions, software and so on, and you can combine it with a lot of different other devices, also like eye trackers, sensors and so on, so very flexible here. We had already, I mentioned it, the dry electrodes. So the dry sensors are simply looking like this. We have these pins that have established the contact between the skin and the system to measure the signals. One system that I want to mention shortly, it's not in the slides right now, is this even smaller wireless system. That's a completely new development that we launched now in this month in principle. It's called Unicorn. It looks a little bit like this Nautilus system, the wireless one, but it's a low-cost solution for around €1,000 only, with 8 channels. Compared to the other systems, that's pretty cheap, I must say, because like this one here costs around only the device around 12 times that, so around €12,000 for this. The other one, only the device. Here it's the PCI system includes already everything for around €1,000. Again, with dry electrodes, with a newer version with the soft electrodes that can also be used with gel. So it's kind of a combination, dry and gel electrodes. Very easy to use. We use it a lot for events, like hackathon events, where people are coming to do some developments together with us. So can also be used, of course. After this short introduction about equipment that we have, I want to pay more focus to the different PCI technologies that we are usually use. So the first one is based on event-related synchronization and desynchronization of the signal. This means activity through when you imagine or think on a movement of your hand, for example. So the idea is this event-related synchronization and desynchronization over your motor area that happens whenever you do a movement. For PCI, it's of course not interesting to see when you do the movement. Our goal is to detect when we imagine the movement. So a typical task is, okay, you tell the subject, now you imagine a movement of your left hand, or now you imagine a movement of your right hand. You do the motor imagery in this period here of around 4 seconds, and this is then used afterwards for the offline classification. So the data is used. We do classification using linear discriminant analysis or support vector machines, and then the people can use the system. This is EEG data, for example, over one position, position C3 it's called. It's over the motor cortex here on the left hemisphere, on the left side of your brain. And this is usually one of the positions that is very active when you are doing a movement, for example. So when I do a movement of my right arm, then my left brain side is active, and especially over this position. Vice versa, when I do a left hand movement, my right side is active. And this is always the same channel. As you can see, there is not really a big difference in the signal, but the subject that was where we measured the signals was doing a movement of the right index finger, directly here in this case. And as you can see, what happens with the signal is the amplitude here before and here after the movement is bigger than here during the movement. So this is the synchronization and desynchronization of the signal. During the movement, the amplitude is pretty low, and this can be used for your classification algorithm, for example. So as I said, movement of left hand, right side is active, so usually around this position. Right hand imagination, the left side is active of the brain, and these ERD patterns can be detected. So my boss developed the first brain-computer interface using that more than 20 years ago. So this picture is pretty old. As you can see, The electrodes that are used here are old. The laptop is extremely old also. But he was one of the first guys to control the arm prosthesis using the brain-computer interface. So he had an accident, and the arm he couldn't move it that much anymore, and the arm prosthesis was allowing him to do a grasping movement to pick up some things with the arm prosthesis, but he needed around I think 2 months to learn how to control it really good. Nowadays we improved that a lot, and we use it for the rehabilitation of stroke patients. So as you can see, the EEG equipment and so on got better, and also the signal processing got way better. So in this case now, the patient after the stroke, it's very often that one side cannot be moved anymore, like the left arm in this case, and he is imagining a movement of the left arm, and then on the screen the avatar shows the movements to him, and also here we do electrical stimulation of the muscles, so also the arm is stimulating and moving, and this generates so-called brain plasticity, so the brain is learning again to control the affected arm. So we had in Austria, in our facility, we measured in the last 2 years, I think almost around 100 patients, and a lot of them, or almost all of them, improved even when they are chronically stroke patients. So usually stroke patients, you have around 1-2 years where you say, okay, when there is improvement, it's good, but usually afterwards you cannot expect any improvements anymore. But we had patients where the stroke was like 5 or 10 years or even more ago, and these patients still show improvement by using the brain. So it's our focus here is that the brain is learning again, so that the brain is trained. Compared with standard rehabilitation methods, usually you check that the arm is moving, so that you train the muscles. Here we really want to train the brain. Besides this first method, there is another one called event-related potentials. I think that's probably one of the most used ones also, where you can use different type of stimulations, like visual stimulation, tactile stimulation, auditory stimulation, and so on. So a visual evoked potential, for example, when we look to this picture, there is this red circle that is popping up, and whenever you look on that, you have a so-called visual evoked potential. So this is the EEG signal. Here is the flashing of this icon, and then you have this typical shape. So you have a negative activation first, then a positive, then a negative again. So this is a normal shape that you can find when you check the signal. To do brain-computer interface, it must be a little bit more complicated. So we have a matrix board like here with characters and numbers, for example, and we want to select one of these characters. So for example, we want to select this one here, and now this matrix is starting to flashing up. So each icon will be highlighted, and whenever we pay attention to one of them, we have a higher positive activation. So we are focusing, and now it's flashing up. So P was flashing up, and then we have a higher activation after around 300 milliseconds. So here was the stimulation, the flashing up. We have the typical shape at the beginning, but usually when you are not paying attention, the signal will stay flat here. But after around 300, when you pay attention, the curve is getting higher here as well. And if you repeat that task a few times, with each repetition, the signal is getting higher and higher. So you can clearly discriminate between the icon where you have paid your attention to the other ones. And this can be used for communication, for example. So when we compare, the green line shows the icon that we were looking at, so we call it the target, and the blue line here is the where all the other icons where we were not paying attention, we call them the non-targets, and you can see clearly the difference. So the non-targets, usually the line stays pretty flat at 0 almost. Here we have clearly the positive activation after around 300 milliseconds. Sometimes a little bit earlier, sometimes a little bit later, but you can clearly see the difference between the two. And this can be used for, as I said, for spelling. So one system that we developed is called Intendix, where you have these icons again on the screen, and they are flashing up row and column wise. So one complete row or one complete column is flashing up. Here we use one small trick by using faces instead of simply highlighting. The human brain wants to detect faces, and whenever a face is flashing up, this P300 is usually higher and easier to detect. So for healthy people, for example, this usually always works with an accuracy of 100% usually. So far I had never anyone who was not able to control this type of brain-computer interface. A similar method, or where we also use this P300, is with tactile stimulation. So instead of this visual experiment, we use here like stimulators that are vibrating. These are like, so this vibration is like in a mobile phone when a mobile phone is vibrating. We place them, for example, on the left and right wrist to do the stimulation. And for example, when we have a third one, you can already do a communication. So when we see, okay, left, right hand, and a third one, maybe mounted here on the back or somewhere else, then you can use a communication. If you say, if I focus on the right hand, that means a yes, for example. If I focus on the left hand, that means no. Then you can do a communication. We tried it once, even with 8 stimulators, like here in the pictures, on all of the fingers, so 4 on one hand each, which is also possible, but of course with more stimulators it's getting harder and harder to discriminate between the stimulations, especially when it's so close, like on the fingers, but you can also distribute them over several body parts. This is used for consciousness assessment. So we have one system, we call it MindBeagle, that is checking in locked-in patients or minimal consciousness patients, how they react on this kind of stimulation. So visual experiments like this matrix board cannot be used with this type of patients because they cannot see or they have their eyes closed. Therefore we use like audio stimulation or this tactile stimulation, for example, because they usually can still feel this activation. So yeah, we call it MindBeagle, as I said. So in principle the amplifier is the same that we use here. We have this tactile stimulation, we have sound stimulation to check simply is there a response in the locked-in patient or in the coma patient by using the brain-computer interface. And one last method that I want to mention is based on so-called steady-state evoked potentials or steady-state visual evoked potentials. So shortly, again, the picture from before, when the icon was flashing up here, or this spot, we have a visual evoked potential. If this flashing is now faster and with a specific frequency, like in this case 7 Hertz, you can find this 7 Hertz in the frequency analysis of your signal again. So this is a signal analysis, and as you can see here at 7, so this is the frequency in hertz. At 7 hertz we have this activation, and also on the harmonics 14 hertz, 21. So whenever you stimulate and you look on this icon, you can find this frequency in the signal again. Of course, with one it doesn't make that much sense. So if you have more, like these two, with different frequencies, you can already select between the two with 17 or 14 hertz. So study showed that in principle it would be possible to have 48 different kind of stimulation frequencies. I think it's a little bit optimistic with 48 because the frequencies are then pretty close, but usually like with 4, for example, it's no problem. So one application that we developed together with a student is the control of World of Warcraft. So therefore I can show you a short video to give you an idea. This is my boss, but that's not so important right now. So in principle, I'll stop shortly now here. My colleague is wearing the cap here. In this case, we place the electrodes in the back because the visual cortex is active usually, and he has to do a training at the beginning. So you see, here is an icon, here is an icon, here is an icon, here would also be an icon, but it's disappeared right now. They are flashing with different frequencies. So each of them have different frequencies, and this green rectangular here shows on which icon he should pay attention in the training. So the system tells him, okay, now you look on this icon, we are measuring the brain signals, and then he's switching to the next icon and so on to do a classification. So I continue here. So now we measure the signals, we do a classification of that. In case of this game control, of course, these arrows are to be to move around in the game environment. This button here or this icon should indicate an automatic action in the game. So whenever you do you select this, the game is or the system is automatically doing something useful in the game environment, like attacking enemies, picking up stuff, for example, from the floor, things like that. And when he is finishing with this training, we can start the game. And now he's only looking on the icons. So when he is focusing on one, and whenever the brain-computer interface is detecting it, you can see this rectangular again. So now it's selected, and as long as he's paying attention, he can move the avatar in the game to walk around. Of course, you can play also with other people that are using the keyboard, for example. Our idea was that people that are affected, who cannot move their arms, are playing this game by simply focusing on the icons on the screen. So he's not doing anything with his arms. He's only sitting in front of the screen and looking on the icons. Okay. Yeah. In principle, that's it from my side. I only want to mention shortly, there are, of course, we have a website where you can find information, gtech.at. There are also a lot of publications online and so on where you can find information. We also have other channels on social media where you can always find some new updates. We also provide courses for teaching purpose, for example, for students. one thing that I want to highlight for you is maybe the PCI Awards. This is from last year, but there is already one for this year also available. So we are organizing always with the PCI Society the so-called PCI Award, where people can submit their work, 2-page description usually, and I think the 12 best projects are printed in a book of Sprenger, and there is also some money to win for the first, second, and third place. So if you have a PCI project in mind, then yeah, there is still time. I think this year the deadline for the submissions is in June, and the presentation will then be at the meeting in Austria with a ceremony. One thing that I want to mention also, this is from last year, is our so-called brain-computer interface designer hackathons. So if you're completely new in this field and you want to get in touch with the topic PCI, then check the website of this Brain.io. There you can find details about upcoming events where we have like 24 hours hacking session. So we will introduce again here brain-computer interfaces. So this is, for example, from a schedule from last year or 2 years ago, where people start at 12 o'clock with their hacking projects, and on the next day at 12 o'clock, the hacking is the development is ending. They present the projects, and then there is usually also some prizes to win. We are cooperating here with IEEE and other institutions. And there are several brain hacking projects available. So in principle, you don't have to be an expert on PCI or so. Most of the projects simply require that you are able to do programming, and of course, you need the interest of for like the brain-computer interfaces. There are also some other projects like artistic projects to design new headsets, for example. But this is another story. So these are some pictures, for example, of such an event. Students were developing applications using our stuff, and colleagues are there for helping people to develop the applications. So if you have time, maybe once you can join one of these events. Pretty nice to get in touch with the technology. That's it in principle from my side. I don't know if people have time, we can maybe try also something out later on. So far from my side, I want to thank you for your